Good everyone, my name is Graphics. Today we want to solve a problem in electrical engineering science, which is electromagnetism, where we are to analyze or solve the question that is displayed on the front of the screen. And the question goes like this. It says three coil X, Y, Z on the core of a rectangular iron with magnetic circuit of length 100 centimeter, cross section of 2 centimeter by 2 centimeter, and relative permeability of 1450. Have a number of turns n subscript x equals to 335, n subscript y equals to 600, and n subscript z is equals to 600. And their respective current flow are I subscript x is equals to 1.5 ampere, I subscript y is equals to 4 ampere, and I subscript z is equals to 3 ampere. A cut section of size 5 millimeter in the core has been made. If I subscript x is flowing in the opposite direction to the others, draw the circuit diagram and calculate the value of the air gap flux, neglecting fringing of flux. Now I'm always saying something. Whenever you're given a question like this, you need to write out your data given to make your work more easier. Now let us write the data given. Now the first thing given here, the data given. Now if you look at the question, it says we have three coils X, Y, and Z on the core of a rectangular iron. Y magnetic circuit of length with a magnetic circuit of length 100 centimeter. So the length of the iron is 100 centimeter. Now I'm using L subscript I as the length of iron to be 100 centimeter. Now you have to convert it to meter. So cent there means 10 raised power minus 2. So you are going to divide this 100 centimeter by 100 to make it 1 meter. So dividing 100 by 100, we're having 1 meter. Now the next one is, it says cross section of 2 centimeter by 2 centimeter. So that is the area. So our area will now be, area will be 4 centimeters square, because when you multiply the 2 by 2, you'll be having 4, then the centimeter times centimeter will give you centimeter square, right? Now you have to convert the centimeter square into meter square. So you have to divide by what? 100 square. Initially, if there was no square there, you divide by 100. But since there's a square there, that means the 100 raised power what? Or power 2. So this is what we have. So this is what we're having, right? Now we'll continue. We said the relative permeability of the iron is 1450. So we write it this way. So we use this symbol, the relative permeability of the iron to be equals to 1450, and have a number of turns. So it has a number of turns which are n subscript x, n subscript y, and n subscript z. So n subscript s means that the number of turns of the coil, the x coil, then the number of turns of the y coil, and the number of turns of the z coil. So we use the x, y, z to represent each of those coils. So we'll write it this way. So that is how we are writing it. Now we move forward. It says, and their respective current, that means the current that is flowing through this coil, that the current flowing through the x coil is 1.5. We'll call it I subscript x. The current flowing through the y coil is 4 amp. We'll call it I subscript y, and that of z is 3 amperes. So especially so write it this way. Now this is what we have here, right? So I subscript x, y, and z. Now, it says there's a cut of size 5 millimeter in the core, right? So we'll call that cut the air gap. So we'll call it the length of the gap, right? So I'm going to write it this way by saying that the length of the gap, L subscript G, and that will be given as this. Now that's 5 millimeter. Now if you convert 5 millimeter into meter, means the milli means divided by 1000, that is 10 to the power minus 3. So you are dividing 5 by 1000 and you are going to be having 0.005. Now after writing that, if you read further, we are told that if Ix is flowing in the opposite direction, so I'm going to write in front of Ix flowing in the opposite direction. So it means that anytime I see Ix will incur a negative sign since it is flowing in the opposite direction. So remember that. So we'll proceed. Now we are now told that draw the circuit diagram and calculate the value of the air gap flux. So we are going to draw the circuit diagram. I'm going to calculate the value of what? The air gap flux. And the formula says we're looking for what? The value of what? This is the flux, but the air gap flux, right? So this is what we're actually looking for. So we need to draw our diagram first and see how it goes. First of all, let's draw a magnetic circuit with air gap. So we want to draw a magnetic circuit with what? With air gap. Now this is the magnetic circuit. I've made a cut here, and that is the length of the air gap, right? So that is my LG. So I'm going to write. Now we have coils, right? 3 coils, A, X, Y, and Z, right? Let me write the coils. Let me draw the coils there. Now this is the coil for what? For X. So this is my I subscript X. That is what? 1.5. Then this is my NA, as N subscript X, which is given as what? 335, right? That is for IX. This is let's do the other one here for the NX, NY. So for this is my I subscript Y, the current flowing through, and that's given as what? From our question is given as 4 ampere. And this is my NY, is given as what? 600, right? So that's the coil for the Y. Then the other one, there's a current for the IZ. So I subscript the current flowing through the Z coil, and this is what? NZ, and that is also 600 tons. So this is what we have. IZ, NZ, right? Don't forget these are what? The LG, the length of the air gap. Then the entire length of the ion is called Li. So this is the magnetic circuit that we are drawing the diagram here, right? So let us start with our calculation. Is that okay? Now we want to calculate. The question is to look for what? To look for the flux of the air gap, right? We want to look at the flux. So let's see how that goes. Now, calculating for flux of the air gap. Now, recall. We know very well that the reluctance, right, the symbol for it is given as X, or use arrow, is equals to what? The MMF, magnetic force, all over what? The air gap. All over the flux, right? So because of what we're actually looking for, we need the total reluctance, right? And and the total magnetomotive force for we to have the air flux of the air gap, as in the flux of the air gap flux. Is that okay? So if I make this man, this is the formula, I'm going to be having this way. So I will now say that the flux of the air gap will now be equals to the magnetomotive force total all over the reluctance, the total reluctance. You call reluctance as the total, as the what? Magnetic resistance. So I will term this my equation 1. Is that okay? So that means for we to have the air gap of this magnetic circuit, you need the total MMF. That means the magnetic force of the X coil and of the Y coil and of the Z coil, right? And the reluctance of the air gap and the what? The metal used for the coil. So let's start. Now the first thing we'll do is to first of all calculate for what? The magnetomotive force of what? Of the total coil in this circuit. So let's see. Now we know that the total, recall, we know that the total magnetic motive force is equals to the magnetomotive force of the coil X plus the magnetomotive force of the coil Y plus the magnetomotive force of the coil Z. Is that okay? But magnetomotive force is equals to the current of the coil times the number of turns. So I will move further by saying that the magnetomotive force total will now give me the current Ix times the number of turns, right? Since this is the S coil, plus the current I subscript Y times the number of turns Y plus the current I subscript Z plus the number of turns of Z. Remember, from our parameter given here, that again we say that what? Ix, the current flowing through the X coil, is flowing in the opposite direction. So we have negative in our Ix. Is that okay? So we'll go back to where we are. So if I want to write it out, I'm going to write it out this way. So this will now be giving me, I'll now put my what? My negative here. Is that okay? So negative Ix from our parameter is giving us 1.5 times Nx, and so will give us 335 in bracket plus the I subscript Y is giving us what? 4 multiplied by N subscript Y, number of turns of the Y coil is what? 600 plus I subscript Z is giving us 3 ampere multiplied by the turns of the Z coil is what? Also 600. Now if I multiply this, I'm going to have 502.5. Don't forget there's a negative there, plus 4 times 600, that'll give us 2400, plus 3 times 600 give us 1800. So we now see that therefore from here our MMF total will now be given as what? If you add everything and subtract from this, you're going to be having 3697.5 unit for MMF is what? Ampere ton. Is that taken? Now they can also write MMF as what? Ampere ton total. So don't get it twisted, because the unit for it is what? Ampere ton. So I can decide to write ampere ton total to represent my MMF total. So it depends on what you want. Is that taken? But this is how we go about it. So this is our MMF. So we've gotten our MMF now. Now the next we'll calculate for is what? The reluctance total. So let's see how that goes. Now, recall we know very well that the reluctance total will be equals to the reluctance of the ion, which is what we're using, plus the reluctance of the gap. Is that okay? Now from here, both reluctance, let's put it both S total, let's put it this way, but the reluctance X total is equals to the length over what? The permeability times the area. You see that? Which can also be given as the length all over your permeability can be given as the absolute permeability multiplied by the relative permeability in the area. Because in our question here, we notice that we have what is called the relative here. So we need to use the other one. Is that okay? So let's start. So if I put it here, I will now say that my S total will now be giving us the length of the ion all over the absolute permeability times the relative permeability of the ion times the area plus the length of the gap all over the absolute permeability times the area. Air doesn't have a relative permeability, so absolute permeability we use for that of air, right? So from here we move forward. We start inputting our value. We are going to be having this to be equals to the length of the ion from our parameter given here. Let's see. The length of the ion is given as what? 1 meter, right? So I'm going to put in my 1 here all over. Now the absolute is given as 4 pi times 10 raised to power what? Minus 7. That is a constant. Multiplied by the relative, which is given as what? 1450 from our parameter. That again, multiplied by the area, which is given as what? 4 times 10 raised to power what? Minus 4. So this is what we have here. Is that again? So from here, this plus the length of the gap is given as 5 times 10 raised to power what? Minus 3. It is given the parameters. Look at what I'm talking about. Look at the parameter. The area that we did earlier is 0.004, using the same 4 times 10 raised to power minus 4. And the relative variability is given as what? 1450. Is that okay? So we'll move forward. From here, we'll now say that all over 4 pi times 10 raised to the power minus 7 multiplied by 4 times 10 raised to the power what? Minus 4. So in so doing, we'll now say that this will now be giving us, if you punch this in your calculator, you're going to be having this to be 1,372,025.371. So we have this 1,372,025, right? 0.371. That is if you punch this in your calculator here. Plus, if you punch this in your calculator, you're going to be having 9, right? 947, 183.94. Now when you add both of them together, you'll be having 11 million. We have 319,000. I'll have 209.31. This is what we have here, right? So if we now want to write it in the standard form, we can now say this is also written as 11.31. You see that? We start counting from the third value. We have 1, 2, 3, 4, 5, 6. So times 10 raised to the power what? 6. The unit for is given as what? 80 per Weber. So that is our total reluctance of that circuit. Now what we're now going to do here is substituting our reluctance and MMF into equation 1. So substituting ST and MMFT into equation 1. So let's do that. So what's our equation 1 that we did earlier? The equation 1 here is given as let's see, this is equal to this, right? So it means that the air gap flux is equals to the MMF total all over the reluctance total. So if I input this here, my MMF total that I calculated for is giving us 3697.5, just like what we did here. This is it here, 3697.5. So divided by we use this particular one here, not this one, we use this, and that will be 11319.209.31. So if you do that, my air gap flux will now be giving us 3.267 times 10 raised to the power what? Minus 4 Weber. So when you press this in your calculator, you're going to have this. So this is the reluctance of this circuit here, and that is what we are told to actually look for. So this is reluctance of what? The circuit. Now we know that reluctance is, it reduces the creation of what? Of flux in the magnetic circuit. And what is the flux? The flux is the number of lines of force in the circuit. Are we together? That's the reluctance. And then the air gap in the circuit usually prevents saturation of flux in the circuit in this point here, right? And also, the magnetic force is just analogous to electromotive force. What does the magnetic force does? It increases the creation of flux in the magnetic circuit. Is that okay? So, brothers and sisters, if you found the video helpful, please don't forget to click on the subscribe button and also click on the notification bell. Thanks for watching.